Hello, hello, AP Chem students. So, these are problems referring to FRQ, free response question number 4 on the AP Chem exam, where you are given the description of a chemical reaction, and then you need to write the balanced chemical equation. Balanced chemical equation. Note that you are to exclude spectator ions. So we're looking at writing what we call in chemistry net reactions. All right, so here's a few we're going to practice here. So let's take a look. I've got 3 columns here. In the AP Chem exam, you'll be given a description of the reaction, and then you'll be asked a question about that reaction. All right, let's see how it goes. So a solution of ammonia is added to a dilute solution of acetic acid. Key word here, acid. As soon as you see the word acid, you're probably thinking to yourself acid-base, and this is definitely an acid-base reaction. Okay. You get credit for just writing the reactants. So, ammonia. No need to put the phases. Everything is an aqueous solution unless you're told otherwise. Ammonia plus acetic acid. Got to remember that formula for acetic acid. There it is. HC3O2. We put one H out front because acetic acid is a weak monoprotic acid. So, acid, base. Ammonia is acting as a base. Again, we think about the Bronsted-Lowry definition. Sorry, it's the wrong place to go. Hydrogen ion is being transferred from the acid to the base. The base is the proton acceptor. The acid is the proton donor. Product of that transfer is that we end up with an ammonium ion, NH4+. It's started out neutral and it accepted a positive particle, a proton as we sometimes call it. The acetic acid lost its hydrogen ion, so now it is a negatively charged ion called the acetate ion. There's the reaction, balanced. Okay. So recognizing acid-base, a big category of chemical reactions. All right, now to the question. Identify the conjugate acid-base pairs. Again, conjugates are substances that are related on either side of the equation. One has the hydrogen ion, one doesn't have it. So one conjugate pair is NH3. It's the base. The conjugate acid is NH4+. So there's one conjugate pair. Ammonia is the conjugate, is the base. Ammonium ion is the conjugate acid. Turn it around. Ammonium ion is the acid. Ammonia is the conjugate base. Get it? Conjugate acid-base pairs. The other conjugate acid-base pair is acetic acid and acetate. So acetic acid now is the acid. It has the hydrogen ion. The acetate ion is the conjugate base. Bingo. So important skill, being able to identify conjugate acids and bases. Remember, by the Bronsted-Lowry definition, we've always got to have a hydrogen ion donor, the acid, and a hydrogen ion acceptor, the base. So just to make sure everybody understands, this is our acid, this is our base if we look at the reaction going left to right. If we look at the reaction going right to left, this is the acid. And the acetate ion is acting as the base. So, base, conjugate acid, acid, conjugate base. Hope that makes a little bit of sense. Okay, more detail than you needed for answering the question on the AP Chem exam. Again, being able to write the reactants correctly gets you some credit. Writing the products correctly gets you some credit. Balancing the equation gets you some credit. Answering the question gets you some credit. This is a place where you're looking to not necessarily get perfection. That's not our goal in the AP Chemistry exam. We're looking to maximize our points. Okay, let's go to B. Solutions of sodium hydroxide. I hope that tips you off. A base, strong base, and our friend acetic acid again are mixed. All right, so we're going to write the net ionic equation. Now, everything you put in the box is what gets graded. So you've got some space on the exam to work outside the box. But anytime you see sodium in an ionic compound, you know it's going to be a spectator. Sodium ion is always a spectator. So we're just going to write sodium hydroxide as hydroxide. That's the key reactive part. The hydroxide is reacting with the acetic acid, so this looks a little bit like the reaction above. If you can't remember the equation for acetic acid, well, at least put something with an H there. You might get credit. You never know. Put a smile on the grader's face. What's the reaction here? Hydroxide is the base. It's acting as the proton acceptor. Acetic acid, again, is acting as the acid. It's the proton donor. Result of that transfer is more of a classic acid-base reaction. We take an H plus and an OH minus, we get H2O, and we get the acetate ion. Bingo. There's our reaction. Okay? Gotten rid of the spectator. This is another acid-base reaction. All right, looking at the question. Acetic acid is a weak acid. They didn't need to tell you that. You knew acetic acid was a weak acid because it was not one of the strong acids. Remember your strong acids. I'm not going to repeat them here. You can look them up. But there's a small subset of 6 strong acids. Strong acids are completely ionized in solution. If you're not a strong acid, you're a weak acid. So if equal volumes of equal molar solutions are mixed, this means essentially we're adding equal number of moles. So we'll have exactly the number of moles of hydroxide as the moles of acid. Some of us will look at that and say, wow, that means that the acid and base completely react with each other. And that's true. The key to this problem, however, is that what's produced here is a weak base. That weak base will produce some hydroxide because weak bases do that. Okay? So therefore, our solution is going to be basic at the equivalence point, and the pH of the solution will be greater than 7. So a couple of things that you might want to memorize. If we have a strong acid and a strong base, pH equals 7 when we mix just the right amounts of both. If we have a weak acid and a strong base, the pH is going to be greater than 7. That's the example we saw here. And then finally, if we have a weak base being titrated by a strong acid, the pH is going to be less than 7. So if we've got strong and strong, that's a true neutralization. If we have weak acid, strong base, we tend towards the strong base side. The ending point is going to be pH greater than 7. Finally, if we have a weak base and a strong acid, the ending or the equivalence point volume pH is going to be less than 7. Okay? We'll talk more about that later. All right. Hydrogen sulfide, that should really be dihydrogen sulfide. I'm not quite sure why they let that slip by. H2S. Why does it have H2S? Well, if you look at this, sulfur is in the same category as water. H2O, H2S. H2S reacts with, bubbled through, okay, that's just in the fancy way of saying reacts with excess potassium hydroxide. So KOH for potassium hydroxide. Potassium we're going to think of as a spectator ion. Therefore, we're just going to write that as OH minus. The reaction is, again, acid-base reaction. Hydroxide reacts with H. Notice that there are 2 hydrogens out front. Dihydrogen sulfide is a diprotic acid. Therefore, I'm going to need 2 hydroxides to react with the hydrogens. The result of my reaction is going to be H2O and 2 H2Os plus S2 minus. Again, we've gotten rid of the the potassium. It is a spectator ion. So you should be smart enough now to be able to pretty quickly eliminate those spectators. If you need to write the overall reaction outside the box to notice that, do that. All right, so we've gotten some credit for this part. This is another example of acid-base, probably our most common type of reaction you're likely to see on the AP Chem exam. Successive ionizations. H2S is what's called a diprotic acid. It has 2 acidic hydrogens. So anytime we have a multiprotic acid, we think of the ionization as happening in a stepwise fashion. Now, the reality is everything happens sort of simultaneously, but H2S first goes to H plus HS minus. It loses 1 proton. And then the HS minus further ionizes to form another H plus S2 minus. Notice that if you add up these two successive or stepwise ionizations, you get the overall reaction that we have over here. Okay? No. All right? Good. All right. Last one here. Barium oxide is added to distilled water. All right. Just something you have to remember. Little yin-yang of chemistry. Metal oxides react with water to form bases, hydroxide bases. On the other hand, non-metal oxides react with water to form acids. So we've got this nice symmetry here. Metal oxides, barium oxide is example. So barium oxide, we've got to be able to write the formula for barium oxide. It reacts with water. No spectators here. And what base is going to be formed? Barium hydroxide, BaOH2. Again, barium is going to have a +2 charge. This reaction is balanced as written. We're in great shape. So there's our reaction. Okay? Barium oxide reacts with water to form barium hydroxide. Metal oxides, which barium oxide is one example, react with water to form the associated metal hydroxide. All right? Important to remember. Is the resulting solution acidic, basic, or neutral? We've produced hydroxide. The solution is definitely going to be basic. OH minus is produced. All right? If they asked you the pH of this solution is going to be greater than 7, it's definitely going to be a basic solution. All right? Excellent. That's 4 for now. And again, this would also be classified as essentially an acid-base reaction. So we're off to a good start here with acid-base reactions. All right. Hope that makes a little sense. See if I can shut this off. Come on. Stop it.